In the past few decades, we've come to realize that our view of the solar system was missing 90% of the picture.
25 years ago, we thought that Pluto was the edge of at least the planets in our solar system. But now we know that there are many more objects like Pluto out there. So not only has the edge of the solar system moved out, but we've become much more aware of how much more we have to learn.
Our newest eyes in the sky peer into these most distant regions of our cosmic backyard.
We are just learning about the vast array of objects in the outer part of our solar system. As our technology has increased, we keep discovering more and more exotic objects, and our picture of what the solar system really is has changed as a result of our ability to improve our eyes.
But it's very old tech that's actually taking us to the edge. When NASA launched Voyager 1 in 1977, they thought it might work for 5 years. 37 years later, the little space probe that could is still sending us mind-boggling information. In August 2012, it was just over 11 billion miles from Earth. It had just left the heliosphere and entered the mysterious heliopause, the junction between the sun's atmosphere and interstellar space.
That heliopause is sort of where those two boundaries meet. It's sort of where our neighborhood kind of stops and sort of the general neighborhood begins.
I was excited when the news came back that Voyager was in the heliopause. This is an entire region of the solar system about which we know almost nothing. And for the first time in human history, we had a robot probe sitting in the middle of it, measuring what was going on around it. It was groundbreaking.
For the first time, we can say, even in a limited extent, that humanity is an interstellar species. We are now out between the stars.
When our game little interstellar probe took a look back at the solar system, it had quite a surprise for us. We had thought the heliosphere was shaped a bit like a comet, with a giant tail extending back hundreds of billions of miles. But Voyager found something new and extraordinary. It didn't find a comet-shaped heliosphere with a giant tail. It found a crescent moon shape with 2 short tails.
It's a really important observation because it teaches us something new. It teaches us what the fundamental shape of the heliosphere is. I mean, a long time ago, we just had the simplest picture, but now we have some detail. We know it's got some structure, and we can start with that and push forward and really begin a deep understanding of the region around the sun.
The tails are jets of energized solar wind.
What causes these jets is fundamentally the tension or the interaction between the background magnetic field of the galaxy and those streaming fast charged particles that are coming from the sun.
Voyager also sent back shocking news about the very edge of the sun's influence.
The heliopause may not be a clear barrier.
It's not just a hard edge, it's not just something really sharp. It's actually sort of a fuzzy extended region. It's hundreds of millions of miles wide.
And right in the middle, Voyager detected something truly weird. A sphere of giant magnetic bubbles.
We expected that the solar magnetic field would just sort of disperse at that point. But that's not really what happened. What they found is that the magnetic field lines from the sun have tangled up, creating sort of a frothy, foamy magnetic structure with bubbles. That was quite a surprise and a very exciting one.
As the sun's magnetic field ripples out, it twists and tangles. The lines crisscross and reconnect, forming giant magnetic bubbles.
Each foamy sphere bubble thing is about 100 million miles across, which is tremendous. That's the distance from the Earth to the sun. And there are thousands of these surrounding the solar system.
No one is sure what these magnetic bubbles do, but it's possible that this cosmic bubble wrap is the first line of defense against galactic radiation, helping protect the solar system from the cosmic onslaught.
Think about how much technology has changed since Voyager was launched and today. No one had phones in their pockets. I mean, no one could even make long-distance phone calls across the ocean without it being a tremendous ordeal. But yet, with this old technology, we're now learning about the very edge of our solar system. Just imagine what we're going to learn over the next 50 years.
Voyager is now beyond the heliopause, but has it really left the solar system?
Not really. There is still plenty of solar system out there for Voyager to pass through. And it will still be going for many centuries, many millennia, before it leaves the solar system proper.
It's outside the sun's atmosphere, but not beyond the sun's gravity.
As we go out, we run into the Kuiper Belt, beyond Pluto's orbit, right? This is very, very far away. And then even beyond that, we have the heliopause, the area of the sun's magnetic field. So you might think that you're at the end of the solar system. But guess what? There's still stuff out there that's gravitationally bound to our solar system.
And every once in a while, something sends that stuff hurtling toward the sun. And sometimes Earth gets in the way. Deep in the outer reaches of the solar system, beyond the last gasps of the sun's atmosphere, we are blind. We simply can't see that far. But sometimes we get messengers from beyond, potentially life-ending messengers, comets.
There's basically two kinds of comets. There's comets that are called short-period comets, and the other kind is called long-period comets.
Short-period comets come from the Kuiper Belt, the disk of space junk just beyond the planets. They travel around the solar system in relatively small circles, returning at regular intervals of 200 years or less. Long-period comets are a bit more mysterious.
The long-period comets can come back around something like every 1,000 years or even 1,000,000 years. And unlike the short-period comets that come in on sort of circles, the long-period ones come in on really plunging orbits, and they can come in from all over the place in all different directions.
And that tells us that they come from somewhere different.
The long-period comets we think are coming from someplace much, much farther away, and it's more like a spherical cloud of very distant things that are now plunging down into the sun every now and again.
When a comet comes in, the sun heats it up. The ice turns into a gas, and the comet loses mass. Over time, these comets will disappear, and yet they keep coming. That means that there must be a reservoir of them out there.
But where is there? Where are they coming from?
One of the first explanations for these strange comets is maybe they're not from our solar system. Maybe the galaxy is full of these icy chunks that occasionally rain down on us. But then we thought, maybe they come from another part of the solar system.
Maybe our whole solar system was surrounded by a ball of junk left over from the very first days of its creation, the Oort cloud.
It was theorized that there must be a reservoir of them, a giant cloud surrounding the solar system with millions, billions, maybe even trillions of these icy bodies.
But we've never actually seen it.
So this Oort cloud, this theorized population of comets, is that. It's theoretical. It's never been directly observed.
The objects in the Oort cloud are so far away and so small and dark that we've never observed something actually out in the Oort cloud. Something has to fall in. So you see things falling in from all of these different angles. From there, you can deduce what must be out there.
But crunching the huge numbers to build an Oort cloud is a staggering task. Meet the Janus supercomputer in Boulder, Colorado.
In supercomputers like these, there are thousands of processors, tens of thousands of computing cores. You can do over 100 trillion calculations per second in a machine like this. And we need this because we're trying to understand the evolution of hundreds of millions of comets over billions of years. Compared to what I could do with a pen and paper, it's no contest.
Using the supercomputer, astronomers can begin to piece together a picture of the giant invisible Oort cloud. And they start with what we can see, the comets that race in toward the sun.
We never see the Oort cloud until a comet comes by. So we need to estimate how frequently one of them is going to be perturbed in just the right way that'll make this close passage by the sun so that we can observe it. We can then work backwards and say, well, we see about one every 10 years of about this size, and then say, therefore, there must be billions and billions of these making up that Oort cloud.
The calculations indicate the Oort cloud is home to 2 trillion icy objects, extending way beyond the heliopause.
It's hard to grasp just how far out the Oort cloud extends, but the edge of it probably is 10,000 times farther away from the sun than the Earth is. 1 trillion miles, a 1 followed by 12 zeros. It's so big, it is so vast, so much larger than the solar system of planets, that if you removed all the planets from the sun, the Oort cloud wouldn't even notice.
So how did the cloud's icy bodies get out here?
A fun way to think of the Oort cloud is that these are pieces of planets that never got used. They really are leftovers.
The Oort cloud actually didn't come with the original package, if you will. The Oort cloud formed when they tried but miserably failed to join the party and become those giant planets, and instead got thrown all different directions, and they now exist halfway to the next star. They're a big, giant spherical distribution.
4.6 billion years ago, our sun ignites. A cloud of dust and gas circles the infant star. Then gravity gets to work, sucking in gas, dust, ice, and rocks to form the infant planets.
The planets formed out of building blocks, smaller chunks of material. Rock, ice, stuff that came together over time.
The frenzy of swirling, colliding matter leaves behind debris as rocky rubble in the asteroid belt and ice in the Kuiper belt. Then Neptune and Uranus got in on the act, scattering the debris out further.
But think about what happens when you have bodies falling together, all kinds of small rocks under the influence of gravity. Some of that will get slungshot around the planet and thrown out into space.
Most of them got thrown out of the solar system forever, but the ones that didn't go on these big, long, million-year looping orbits, and that's the Oort cloud.
Billions of icy rocks were thrown out in all directions until a ball of debris formed around the whole solar system.
The Oort cloud comets are dinosaur bones of solar system formation. Contained in them are the ingredients that went up to make our planets.
They are a time capsule of what the solar system was like 4.5 billion years ago.
Most of the Oort cloud objects will stay in the icy cloud forever, orbiting the distant sun. But a few get nudged loose, and the sun's gravity pulls them inwards, like moths to a flame.
And such a comet can sneak up on you and you won't even know it's there.